Hello students, let's start today with ionization of acids and bases. So acids like HCl, HNO3 and H2SO4 when dissolved in water dissociate almost completely, thus producing a large number of H plus ions, and hence these acids are called strong acids. On the other hand, acids like CH3COOH, HF, H2CO3, H3PO4, etc. dissociate only to a small extent in the aqueous solution, giving small amount of H plus ions and hence are called weak acids. Similarly, bases like sodium hydroxide and potassium hydroxide dissociate almost completely in aqueous solution and thus produce a large number of OH minus ions and are called strong bases. Whereas bases like ammonium hydroxide, calcium hydroxide, aluminum hydroxide, etc. dissociate to a very small extent in aqueous solution and therefore are called as weak bases. Thus, the dissociation of weak acids or bases in water can be represented as an equilibrium process. For example, CH3COOH plus H2O gives CH3COO minus plus H3O plus. NH3 plus H2O gives NH4 plus OH minus. In general, if a weak acid is represented by HA, its dissociation in water can be represented by the equilibrium HA plus H2O gives A minus plus H3O plus. When I apply the law of chemical equilibrium, the expression for equilibrium constant will be K equals to molar concentration of A minus into molar concentration of H3O plus divided by molar concentration of HA upon molar concentration of H2O. Thus, you can calculate the equilibrium constant. As H2O is solvent, its concentration is large and it remains almost constant. So KH2O is equal to Ka, called dissociation constant of the acid. So Ka equals to molar concentration of A minus into molar concentration of H3O plus upon molar concentration of HA. Alternatively, we can write Ka equals to H plus molar concentration into A minus upon molar concentration of HA. So here in this chapter, we will be using H plus and H3O plus almost in the same terms. So knowing the value of dissociation constant of the acid Ka and the concentration C of the weak acid HA taken, the concentration of H3O plus or H plus in the solution can be calculated as follows. So let the initial concentration of HA be C moles per liter, then X moles, suppose it gets reacted, then concentration at equilibrium HA remaining is C minus X and H plus and A minus formed is equal to X molar. So when I calculate the dissociation constant of the acid, that is Ka equals to X into X upon C minus X, that is equal to X square divided by C minus X, where X equals to H plus at equilibrium, that is equal to amount of acid dissociated. So Ka equals to X square divided by C minus X. Usually X is very small as compared to the initial concentration C. So X is neglected in comparison to C. So the equation is simplified to the form Ka equals to X square upon C, or X equals to root over Ka into C. However, it may be pointed out that if X is more than 5% of C, X cannot be neglected in comparison to C, and the equation has to be solved as a quadratic equation to get the value of X. Similarly, the dissociation of a weak base in water can be represented by the equilibrium BOH plus aqueous gives B plus plus OH minus, and the dissociation constant of the weak base Kb will be equal to molar concentration of B plus into molar concentration of OH minus divided by molar concentration of BOH. So that is how we can calculate the value of Kb. Now look at the sample problem. The question is calculate the H plus ion concentration in 0.10 molar acetic acid solution given the dissociation constant of acetic acid in water is 1.8 into 10 raised to minus 5. So let's see the dissociation of acetic acid. CH3COOH gets dissociated into CH3COO minus plus H plus. Now initial concentration of acetic acid is given here as 0.10 molar. And concentration at equilibrium, suppose X moles of it gets dissociated, then concentration at equilibrium remaining acetic acid is 0.10 minus X molar, and CH3COO minus and H plus formed is equal to X molar respectively. So dissociation constant Ka is equal to molar concentration of acetate ion into molar concentration of H plus ion divided by molar concentration of acetic acid. So we'll put the values. Ka is here given as 1.8 into 10 raised to minus 5. CH3COO minus we assumed here as X moles. H plus also X moles. So X square upon 0.10 minus X. We'll calculate the value of X square and it comes out to be 1.8 into 10 raised to minus 6, or X equals to root over 1.8 into 10 raised to minus 6, and its value comes out to be 1.34 into 10 raised to minus 3 molar. That is, X here is H plus ion concentration, which is equal to 1.34 into 10 raised to minus 3 molar. Hope you have understood this problem. Let's now come to the dissociation constant and ionic product of water. Ionic product of water is represented by Kw. So we'll see here the pure water we already know is a poor conductor of electricity. This shows that water is a weak electrolyte and it gets ionized to a very small extent. H2O gives H plus plus OH minus, or H2O plus H2O gives H3O plus plus OH minus, and this ionization is called as your self-ionization of water. So when you apply the law of chemical equilibrium to this, we get K equals to H plus into molar concentration of OH minus upon molar concentration of H2O, where K is the dissociation constant of water. Now, ionic product of water may be defined as the product of the molar concentration of H plus ions and OH minus ions, as H plus ions in water exist as H3O plus ions. Therefore, ionic product may also be defined as the product of molar concentrations of H3O plus and OH minus, that is, Kw is equal to molar concentration of H plus into molar concentration of OH minus, or Kw is also equal to a molar concentration of H3O plus into molar concentration of OH minus respectively. Ionic product of water is constant and constant temperature, and its value at 25 degrees Celsius, that is 298 Kelvin, is found to be 1.008 into 10 raised to minus 14. So Kw at 298 Kelvin is taken as 1 into 10 raised to minus 14 for simplicity. It may be carefully noted that dissociation or ionization constant of water is different from ionic product of water. Dissociation constant is Kw and ionic product of water. The two terms K and Kw are two different terms which will be seen. K equals to Kw upon 55.55, or Kw is equal to K into 55.5. By substituting H plus into OH minus is equal to Kw and H2O as 55.55 in the equation 1, we get K equals to 1.8 into 10 raised to minus 16 respectively. So ionic product of water is defined as the product of molar concentration of H plus and OH minus ions. Next we come to a very important terminology, and it is pH. pH is a convenient representation of H plus ion concentration or H3O plus ion concentration. So just now we saw that Kw for water is equal to H plus or H3O plus into OH minus, and its value is at 298 Kelvin taken to be 1 into 10 raised to minus 14. So pH of a solution is defined as the magnitude of the negative power to which 10 must be raised to express the hydronium ion concentration. Or we may also define pH as negative logarithm of hydronium ion concentration or negative logarithm of H plus ion concentration. So equation is pH, for pH is written as pH is equal to minus log of H plus. So pH is also defined as the logarithm of the reciprocal of H3O plus ion concentration. Now look at, this is the pH scale, and pH scale ranges from 0 to 14, in which 7 is the neutral part, and from 8 to 14, character which is shown is basic in nature, and from 0 to 6, the character shown is acidic character. So here acidic character, 0 to 6 basic character, 8 to 14, and in between is your 7, and it is neutral species. Water usually comes under it. Basic, all bases, sodium hydroxide, potassium hydroxide, etc. Acids, all acids, hydrochloric acid, H2SO4, sulfuric acid, nitric acid, etc. They show acidic behavior. So this is the arrangement of pH scale. We have pH is equal to minus log H plus. Similarly, we can also have POH equals to minus log of OH minus. Also, you can calculate the pKa value, which is equal to minus log Ka. pKb equals to minus log Kb, and pKw equals to minus log Kw, where Ka and Kb are the ionization constants of acid and the base respectively, and Kw is the ionic product of water. Let's see now the relationship between pH and POH. Just now I said pH is equal to minus log H plus and POH is equal to minus log OH minus. Since molar concentration of H plus into OH minus is equal to Kw, which is equivalent to 10 raised to minus 14 at 25 degrees Celsius. So log H3O plus plus log OH minus is equal to log Kw, which is equal to log 10 raised to minus 14, which comes out to be minus 14. Or minus log H3O plus minus log OH minus is equal to minus log Kw, which is equal to 14. Or pH plus POH is equal to pKw, which is equal to 14. So keep in mind this formula, pH plus POH is equal to 14 there, and its value is equal to the value of pKw, that is 14. So this formula will be applicable for you in the numerical of this pH problems. So let's see ahead the numerical problem. Before that, let's see the relationship between Ka and Kb or pKa and pKb values. So if you consider a weak acid HF, its conjugate base is F minus. They dissociate as Ka equals to H plus into F minus upon HF. F minus again reacts with water and forms OH minus plus HF, and Kb for this is equal to OH minus molar concentration into HF divided by F minus. And when I multiply equation 1 and 2, we get Ka into Kb is equal to Kw. So log Ka plus log Kb is equal to log Kw, or pKa plus pKb is equal to pKw, which is equal to 14, 1, 4, 14. So pKa plus pKb is equal to 14. Now let's see the application and numerical problems of this pH. So the first problem is the simple one. It is the concentration of hydrogen ion in a sample of soft drink is 3.8 into 10 raised to minus 3. What is its pH? So first of all, you will put the formula there. pH is equal to minus log of H plus ion concentration. This H plus should be written always in big bracket because this shows the molar concentration of this H plus ion. So here in this question, H plus ion concentration is given here as 3.8 into 10 raised to minus 3. So we'll put the value pH is equal to minus log 3.8 into 10 raised to minus 3, which is equal to, in log we know multiplication becomes addition. So this becomes minus sign is outside the bracket, log 3.8 plus log 10 raised to minus 3. So plus log 10 raised to minus 3, this minus 3 comes before this log, it becomes plus minus 3 log 10. So plus of minus is minus and log 10 value is 1. So we get here is equal to minus, when you look into the log table, the value of 3.8, it comes out to be 0.58 minus 3 here, minus 3 log 10. So log 10 value is 1, minus 3, we get the value. So on subtracting minus 3 from 0.58, I get the value as minus 2.42. So minus of minus 2.42 becomes plus 2.42. So pH of soft drink is equal to 2.42. That's the answer. Hope you have understood this problem. Solve it and see whether you are able to solve or not. The next problem is assuming complete dissociation. Calculate the pH of the 0.003 molar HCl solution. Again, you'll put it in this formula. pH is equal to minus log of H plus ion concentration. And here H plus ion concentration is given here as 0.003 molar. So you convert this first to scientific notation. It comes out to be 3 into 10 raised to minus 3. You can see 1, 2, 3 places right I have shifted. So that's why here it comes out to be 10 raised to minus 3. So H plus ion concentration given is 3 into 10 raised to minus 3 molar. So put it in the formula, pH is equal to minus log 3 into 10 raised to minus 3. Minus here, as I said, multiplication in log becomes addition. So minus sign is there outside the bracket, log 3 plus log 10 raised to minus 3. The value of log 3 is 0.4771 minus 3 log 10 value is 1, so it comes out to be minus 3. So on subtracting, we get the value minus 2.5229. Minus of minus becomes plus, so the answer is 2.52 respectively. Approximately it is 2.52. Hope you have also understood this problem. Look at the third one. These two were easy ones. Look at the third one. The third one is the question, assuming complete dissociation, calculate the pH of 0.005 molar NaOH solution. So here sodium hydroxide solution, you need to calculate the pH of it. So sodium hydroxide actually gets dissociated to sodium ion and hydroxide ion. So here if NaOH solution is given, we get here the OH minus ion concentration. So OH minus ion concentration given here is 0.005 molar. When I convert this to scientific notation, it becomes 5 into 10 raised to minus 3 molar. Correct? Just now I told molar concentration of H plus into molar concentration of OH minus is equal to 10 raised to minus 14, or H plus ion concentration is equal to 10 raised to minus 14 upon molar concentration of OH minus. So firstly, I would like to calculate the H plus ion concentration by substituting the values. 10 raised to minus 14 divided by 5 into 10 raised to minus 3. And I get the H plus ion concentration here as 2 into 10 raised to minus 12 molar. This is one way of solving. And then I can calculate the pH. pH is equal to minus log of H plus ion concentration. So here I got the value of H plus as 2 into 10 raised to minus 12 molar. So I'll put the values. pH is equal to minus log 2 into 10 raised to minus 12. Minus sign is outside the bracket. Log 2 plus log 10 raised to minus 12. Value of log 2 is 0.3010 minus 12 log 10. Log 10 value is 1, and on substitution, subtracting, we get the value as 11.699. Approximately the answer is 11.70. This is one way of solving. Look at the other way also. Both the ways are easy. Whichever method you like, you can solve and calculate the pH. This is one way. The second way is, here you can calculate POH first by putting in the formula POH is equal to minus log of OH minus ion concentration. So it equals to minus of log 5 into 10 raised to minus 3. The value of log 5 is 0.6990 minus 3 log 10. So log 10 value is 1. So minus 3 into 1 is minus 3. So on subtracting, I get the answer here as 2.301. So this is POH which I get, 2.301. I have to calculate the pH of the solution. So you will put in this formula pH plus POH is equal to 14, or pH is equal to 14 minus POH. 14 minus 2.301 gives you the value 11.699. Approximately your answer is 11.70. So this is another way which you can solve. Either of the way you can solve and calculate the pH of the solution. Hope you have understood. Now look at question 4. Question 4 is, calculate the hydrogen ion concentration in human blood whose pH is 7.38 and lemon juice whose pH is 2.2. So in this question, you have been given the pH and you have been asked to calculate the H plus ion concentration. So let's see one by one how to calculate. The first part you see, pH of human blood is given here as 7.38 and you need to calculate the H plus ion concentration. Firstly, you put the formula pH is equal to minus log of H plus ion concentration. So after putting this formula, pH is given 7.38 and you need to calculate the value of log H plus. So bring this log H plus to the left hand side, it becomes log H plus, and this negative sign is carried to the right hand side is equal to minus pH. So this is equal to minus 7.38. So in the question, log H plus is equal to minus 7.38. So remember, in log, the mantissa part is never negative. You need to make the mantissa positive by adding plus 1 and minus 1 to the terms. So here you see, I have added minus 7.38, plus 1 and minus 1. So when I add plus 1 and minus 1 to the digit 7.38, minus terms together I'll add. Minus 7 minus 1 is 8 minus 8. So this 8 is there on the characteristic digit. So I put 8 bar on it. And from this plus 1, I'll subtract minus 0.38. You can see this plus 1, I am subtracting this minus 0.38. So 1 minus 0.38 gives you the value of 0.62. So you need to first make this characteristic digit negative, and mantissa in log is never negative. You need to make it positive always. So for making positive, I add plus 1 and minus 1 to the terms, and I get the value of log H plus is equal to 8 bar 0.62. Then I'll find out the value of H plus, which is equal to anti-log of 8 bar 0.62. And in the anti-log table, I'll see the value of 0.62. It comes out to be 4169. And you see this number which is present in the characteristic digit, that is simply 10 raised to that number, 10 raised to minus 8. And from one decimal place left to right, I put the decimal point always. So my answer is 4.169 into 10 raised to minus 8. Hope this is clear. Let me tell you the second one so that it will be more clear to you. The second part of the question was calculate the pH of, calculate the H plus ion concentration of lemon juice whose pH is given there as 2.2. So we'll put in the formula pH is equal to minus log of H plus. Log H plus is equal to minus pH, which is equal to minus 2.2. So remember, the mantissa part is never negative. I need to make it positive. For that, I'll add plus 1 and minus 1 to the terms. And these two minus terms I'll add together. Minus 2 minus 1 becomes 3 bar. And negative sign comes on the characteristic digit. And from this plus 1, I subtract this 0.2. So plus 1 minus 0.2 is equal to 0.8. So I'll calculate the value of log H plus, which is equal to 3 bar 0.8. And H plus will be equal to anti-log of 3 bar 0.8. When you look into the anti-log table, the value of 0.80, its value is 6310 into the term which is present in the characteristic digit 10 raised to minus 3. And one decimal from left to right, always I put the decimal point and my answer comes out to be 6.310 into 10 raised to minus 3. Practice, you can all understand the concepts there. More practice is necessary. Now look at this question 5. It is a little tricky question. And the question is, calculate the pH of 10 raised to minus 8 molar HCl solution. So you see here, H plus ion concentration is given as 10 raised to minus 8 molar. So pH is equal to minus log H plus minus log 10 raised to minus 8. And its pH values comes out to be 8. But since it is hydrochloric acid, it is an acid solution, we cannot get the pH above 7. It should be below 7. So here we are getting 8. So since pH cannot be 8, it should be less than 7. So the solution, as the solution is acidic in nature, we should get this value less than 7. Now why we are getting here 8? Because here we cannot neglect the value of H plus ion concentration that is coming out from that of water. Since this is HCl solution, I need to take into account the H plus ion concentration from that of water, and thus we can calculate the pH of solution in this way. From HCl, H plus ion concentration is 10 raised to minus 8 molar. From H2O, H plus ion concentration is 10 raised to minus 7 molar. Total H plus ion concentration will be 10 raised to minus 8 plus 10 raised to minus 7, which is equal to, if I take 10 raised to minus 8 common, 1 plus 10. So 11 into 10 raised to minus 8 molar. This is the H plus ion concentration. Then I'll put in the calculation pH is equal to minus log of H plus. This is the formula which I'll be applying for calculation, equal to minus log 11 plus log 10 raised to minus 8. So log 11 value is 1.0414 minus 8, and minus of minus, its value comes out to be 6.9586, and approximately its answer is 6.96. So here you see in this case I'm getting below 7 the value of pH. Since this is acidic solution, I should get the value of acidic solution below 7 and not greater than 7. If I'm getting 8, it means it is for basic solution, which is not possible for HCl solution. Similarly, let's see the next calculation for base. Question is, calculate the pH of 10 raised to minus 10 molar NaOH solution. So here OH minus ion concentration is given as 10 raised to minus 10 molar, and it has come from NaOH solution. I need to consider the OH minus ion concentration that comes from water. and it comes out to be 10 raised to minus 7 molar. So I'll first calculate the total OH minus ions. It is 10 raised to minus 10 plus 10 raised to minus 7. So if I take common 10 raised to minus 7, it's 10 raised to minus 3 plus 1. And I get total OH minus ions here as 1.001 into 10 raised to minus 7 molar respectively. So POH is equal to minus log of OH minus ion concentration. On solving, I get the value of POH here as 6.9986 respectively. So pH, I know the formula. pH is equal to pH plus POH is equal to 14, or pH is equal to 14 minus POH, which is equal to 14 minus 6.9986, and its value pH comes out to be 7.0004 respectively. So the pH of basic solution should be greater than 7, and pH of acidic solution should always be less than 7. That is the concept you have to remember in your mind. If you're getting in base, if you are getting the pH less than 7, it's wrong. And if you are getting in acid greater than 7, it is wrong. So there you need to consider the H plus ion if it is a case of acid, or OH minus ion if it is a case of base, for solving the numericals, and then calculate the pH of the solution of an acid or a base. That is how you will be solving. So thank you, children. In the next class, we'll be dealing about that of ionization constants of acids and bases, and in detail. Till then, have a nice day.